So now in this video, I kind of named it Reading Schematic Diagrams with Circuit Fragments because ultimately everything in electronics involves circuit fragments, different parts of a circuit doing a specific thing. And we're going to look at controlling voltage, and generally there's parallel elements to that. So I added parallel into the title there. So we're going to introduce some new components for this video series. If you're studying schematics, odds are you've already studied components, but we're going to look at the Zener Diode and the capacitor. We looked at regular diodes and LEDs in the first video, and so I have some circuits down here, a couple circuits, and really it's basically the same circuit, but what it's going to do is we're going to look at polarity indicator circuits. So we're going to use a couple LEDs to tell which side of the power supply is powering which side of the circuit. And so it's pretty straightforward. We're going to use 9 volts. I have my bench power supply set to 9 volts, and you can see here that I'm going to use a 470 ohm resistor to protect the LEDs from 9 volts. This is a 470 ohm resistor. It could be higher. The LEDs just won't be as bright. We could use a lower voltage and then use a lower value resistor. This isn't the absolute minimum you should use, but it's about the minimum. So with 9 volts, I try to always use 470 ohms of resistance as much as possible. But we could go 5 volts, 220 ohms, or whatever. That's going to be another big theme of this video, is substitution of components, power supply, and whatnot. Because generally, schematic diagrams are just tools to teach you about circuits. You ultimately need to be able to modify them sooner or later. So there you can see the positive side of the power supply. We're connecting a resistor. Other side, we're coming here for LEDs. So I have one space between this jumper and that, because as you can see, the LEDs are right next to each other. They're leads. So the green one, we're going to put the anode, that's the long lead, towards the positive side, so directly to the resistor. Short lead, the cathode, we're going to connect directly to the negative side. So that will make it forward biased so that it can light up. Pretty straightforward. Let's move it over here and plug that in. So you can see those connections there. Now we're going to put a red LED parallel to it, but you will notice that the cathode, the short lead, and the side with the flat edge, if you trimmed the 2 wires, that's going towards the positive side. The long lead, the anode, is going towards the negative side. So long lead down right there. And we are going to turn the, or actually we got to plug the power in. So I have these coming from the bench power supply, these alligator clips. I just clipped them to jumper wires there. We're going to put the red one, the positive side, to the red rail there, and the blue one to the negative rail right there. And there you can see the green LED lit up. Now green LEDs are naturally brighter than red LEDs. It has less current going through it than the red one will. We'll look at coming up. And so we could also, or instead of a resistor there parallel, a couple of resistors there, use a slightly higher value one for the green one. And I should have did that for this diagram, but I didn't think of it till after I printed it out. But in any case, you could use a higher value resistor for the green LED than the red LED because it's just naturally brighter. So you can reduce the current even more for the same, to try to get the same brightness, I should say. So in any case, we have the green LED lit up. Not surprising, it's forward biased. So the reason why this is called a polarity indicator, though, you can see that with the exact same circuit, we can easily flip the polarity of the power supply. So in this case, the main voltage switch is actually the power supply for this particular circuit for this demonstration. So now maybe green means maybe you have it wired so that when you see a green light, you know the power supply, the battery or whatever is connected properly. We're going to miswire this according to the breadboard. So breadboards are not polarized. They just give you blue and red there to help keep track of where you have everything wired. So you're supposed to put positive to red, negative to blue, but you don't have to. The board doesn't care. There we go. We plugged it in. So now we have the red LED lit up. Red LED is forward biased. It has the same resistor protecting it, with the same power supply, it's not near as bright. It even blocks less voltage, so even less or more current is going through it than there was the green one. That's stuff to look at in more detail later. We're mostly focused on the wiring here. But there you can see the red LED is lit. So maybe you would wire something like this up to a battery and use a higher value resistor so you don't waste much battery capacity. But that way you could tell if a battery was wired backwards or something before you attach a sensitive circuit to it. You know, that's one way this could be used. So, in any case, we're going to move on to the next topic. And so now, we're going to be looking at the capacitor in schematic. So, there is the schematic symbol. This one is for non-polarized, and that one is for polarized. And so, I wrote small values, large values there. The main thing is that polarized capacitors can only be charged in one direction. So, you can see we got a couple plates there, and you attach a power supply to the component in some way, and that power supply moves charges. So the side of the capacitor connected to the positive side of the power supply becomes more positive, and the side connected to the negative side of the power supply becomes more negative. It builds up that charge. It can be released for later. So with the polarized capacitor, you have to charge the side that's labeled as more positive. In this case, it's not the labeled side. You have to attach that to the positive side of a power supply, and the side, you can see a dash is there. That indicates the negative. It also has a shorter lead than the positive side. That has to be more negative. And so you can discharge it to 0 volts, but you never want to reverse charge it. Non-polarized capacitor. So this is a 470 microfarad. Comes from my Joe Knows Electronics kit. It's my largest one. This is my smallest polarized one right there. So it looks exactly the same, but smaller for the most part. That's 2.2 microfarad. So my next smallest capacitor are these. So these are not polarized. So it's mostly the value of capacitance that will determine whether a capacitor is polarized or not. But if you have in some way a 1000 microfarad capacitor that is not polarized, you can still use it in the circuit. So the polarization is a limitation. So that's just the way they have to make them, where the larger value ones, they only accept a charge in one direction. This will take a charge in either direction. That's 0.47 microfarad. This is my smallest value altogether in the Joe Knows Electronics kit, 4.7 picofarad. So this one has about 100,000 times the capacitance of this one. But that's not our main concern now. We're going to look at it in the schematic diagram. So I'm going to get it ready, but we're going to look at this circuit right here. And now I'm ready. So we're going to use a different power supply here. We're going to use my new portable power supply. You can see the plugs come there. There's alligator clips on the other side. We can set the voltage and the maximum current. So I made sure this will not output more than 5 amps right there. And we're going to be dealing with a lot less than 5 amps. So let's get to the build. We have in this circuit a switch, and I didn't mean to have it on the board yet, but we got the switch there. One side of the switch is a push button switch. We went over this component in the last video. Those top 2 pins are always connected. The bottom 2 pins are always connected. It kind of tries to squeeze itself out of the board. But there you can see that's connected to the positive side of the power supply. And in this circuit, it's important that we have the polarities right, because once the switch is closed, we will have the battery, the capacitor here, directly connected to the power supply. So this is a 1000 microfarad capacitor. I said in the last video my largest was 470 microfarad. That was for that particular kit. So I do have 1000 microfarad capacitors from some other kits, but it's polarized. So we got to make sure the other side of the switch from that side is where the positive side of the capacitor is connected, and then the negative side we can put directly to the negative rail right there. And so pretty straightforward, not too bad right there. So when we close the switch, we'll get an instant charge. We'll see that coming up. Now, parallel to the capacitor is going to be, in this case, a 1 kilo ohm resistor. It just kind of helps to make the math easy. So I grabbed it from this biggie. You can see it's 1K there. After a while, you get an idea what the value is by the colored stripes on there. Worst case scenario, you take a multimeter to measure that. So we're going to take the 1 kilo ohm resistor right there and connect it to the same spot as the positive side of the capacitor. Let me see if I can get the light a little bit better. That angle you can kind of see back there. So we're going to put that there and then come down here one spot away from that jumper, just because I kind of wanted to space things out so it's a little easier to see the connections. So we're one spot away from the jumper, and I wrote blue LED on there. I'm going to use a green LED. Remember, we're going to look at substitutions in this video, and the green LED acts a whole lot like the blue LED in relationship to the red LED. So they act basically the same, but the green and the blue LED block some more voltage than the red one, but still light up brighter. So we're going to press the switch, and I have to turn the power supply on first actually. So there you can see it is off. That is the output. There's an on-off button right there, and so I'll come down, I'll press the on-off button, and now you can see on, and we have the voltage. So that is the output right there that we plugged to the rail, and I clipped the alligator clips to the jumper just like we did before with the other power supply. Now I hold the switch, the LED turns on, the capacitor charged instantly. I release it, you can see that it goes off. Also, we can look at the current being demanded from the power supply. So right there, it's not showing anything, which the current is very, very low. It may be below 1 milliamp. So that's 1 milliamp, 10, 100, and then 1,000 if there was ones there. But in any case, you can see as soon as I let go of the button, the capacitor, it built up a charge instantly. So in this case, we get an instant charge, but the discharge takes time. So there's a changing voltage right now. It's dropping. So we're only dealing with 3.3 volts. This block's almost 3 volts. And so we're dealing with very little currents. Let's see how this fares with the red LED and do the same thing. And you see the LED is not near as bright. It's still not showing any current, and but it's letting more current go through it, even though it's not as bright, and it's turning off quicker. So we substituted the red LED for the green one. Now let's change the voltage. That's why I wrote on here 3.3 volts to 12 volts. That's with a 1 kilo ohm resistor. It will protect an LED from about 12 volts, and you may not want to go much higher than that. But in any case, to change this, it's pretty easy. I'm going to turn the output off again right now. Why not? And we hit set. Let's see if that plastic film, yeah, that plastic film makes it worse. So I was going to leave a protective film on there, but in any case, we will go down to 12. We could even leave it 12.3 if we wanted, but we got the 2 there, and now we got the 1. So I really like this portable power supply, and we're done. That's it. Just a few presses right there, and we have to attach one of the LEDs. Let's do the green LED again. So it's forward biased. That's the main thing. A lot of times if a circuit doesn't work, I'm going to turn on the output there. Remember, we got to hit the button. This power button does not turn the unit on and off, just the output on and off. You actually have to unplug it to completely turn it off. So there we go. Now you see a much brighter green LED because there's a lot more voltage, and you can even see the current on there. So we probably have 8 milliamps of current flowing through here. You can see how bright it is. Now it's going to stay bright a lot longer. So we charged up the capacitor to 12 volts, and it's going to keep discharging. The LED block's about 3 volts, and so it's going to probably discharge 9 volts down to 3 volts, and then probably level off somewhere around there. So maybe 2.5 or something. We could take those measurements later and see exact values. Now let's compare that with the red LED, which you're going to see it light up. You may have saw it light up. I could tell in person it lit up, but you may or may not have been able to see on camera. But now we press it again. Now you can see there's even more current going through it. Not a lot more, it doesn't look like, but 9, and it's nowhere near as bright. So that's the thing. At the lower voltages, you may need a green or blue LED for a particular setup for brightness. Even though it's using less current, there may be so little voltage that you need a really bright, obnoxious LED. Whereas with like 12 volts, this red LED is just fine. It's probably going to be bright enough, even with a 1 kilo ohm resistor right there. So that was a couple of adjustments. In fact, let me swap out this capacitor. Alright, I got a capacitor from this big, so it's 0.47 microfarad. They are not polarized. I'm going to pluck this one out of there, and we're just going to swap it. I'm going to put this right in the exact spot. It doesn't matter if I put it that way or this way. Turn it around. You didn't see me turn it around though, but it doesn't matter which way I put it because it is not polarized. So the capacitor does not care. It will only get a charge in one direction, but it doesn't matter which way we put it in. That's the main thing. So now I press that. You see the red LED turns on just like it did before. We are dealing with 12 volts like we did before. I let go, it turns off practically instantly. So it didn't turn off instantly, but there's hardly any charge here compared to the other one that we used right there. So if you don't want it to shut off suddenly, sometimes like when you're pressing the switch, you might kind of just miss a little connection once in a while. This may cover the gap, it may not. So that would be called a smoothing capacitor. Sometimes these power supplies kind of have a little ripple. Their voltages change a little bit. Capacitor like this will probably be able to pick up the slack and hold a steady voltage like that. So there are uses, that's why you'll see capacitors like that. In this particular circuit, it will not fade off the LED like the large capacitor did nicely. So again, when you see circuits like this, pay attention to their electrical properties more than anything else, because odds are you're going to have to make a change. But here you can see we have practically no voltage. In fact, let's get the multimeter really quick. Alright, I grabbed an oscilloscope and I lowered the voltage to 6 volts. That's because we only got so many divisions there, and that's 5 volts. That should not be 5 volts. Let's change this to 1 volt right there. And so what I'm going to do is we still have the little capacitor there, about half of a microfarad. So very, very small amount of capacitance. But you can see I press the button there. We have that voltage jump up there. So that should be about 6 divisions. 1, 2, 3, 4, 5, 6. It's easier to see it in person than through the camera. And now when I let go, there you can see a drop and a curve right there. So it is pretty dramatic, as you can see right there, because it is a low value capacitor. So I'm going to pluck it out and take the 1000 microfarad capacitor. So this has 2000 times the capacitance. I'm going to make sure it's discharged. There may be a pop. There we go. We were dealing with 12 volts before, but in any case, no pop. We made sure it's discharged. It's good to always discharge them. If you are not sure how charged they are, use a resistor to discharge them. And if they have a high voltage or something, use a resistor that can handle the current to slow down how fast it discharges so it's not instant. But in any case, that will prevent a big pop or whatever, electrical spark. So now we're going to hold the button again. You see an instant jump in voltage right there. The capacitor charges instantly. It's holding a voltage. So the red, I'm going to call it a probe. It's an alligator clip, but I clipped it to this wire. It's to the positive side of the capacitor. Now when I let go, now you can see that the curve goes slow. And but it's still the same curve. And you also notice here, it is not going right to 0 volts. That's 1, 2 volts. These LEDs, they block voltage even while they're forward biased, even while they are set to conduct. And so at lower currents it goes down a little bit, but there you can see it's pretty leveled off. It's not down to nothing. I will do a quick short circuit if I can, connecting the wires there, and finally you see it drop down once I get a good enough connection, direct connection from the wires to the negative rail. So that didn't go terribly well, but in any case, let's give it a quick one, and it comes down. So there you can see that curve path. As long as I hold the button down, press the button, voltage shoots up to the power supply voltage. It holds until I let go again. So sometimes you'll see little graphs and stuff like that next to schematics to give you the electrical properties, because they are important. So now I'm going to remove this. The voltage is going to hold even better, and I'm going to swap it out with the red LED. Again, putting it forward biased right there, and I expect a little more of a drop, but we're going to quickly give it a long pulse right here. You can see the LEDs on, and now because it's a larger value capacitor going through 1 kilo ohms of resistance, it's dropping a little bit below that 2 volts. So these block a little bit less, the red LEDs block a little less voltage than green or blue ones. So you can see it is lower there now, and over time it may let a little trickle of current go through and discharge it a little bit more. But in any case, that's something you may see added to capacitors, an actual little graph drawn out to tell you the electrical properties. In this case, it is voltage. Current is also important. It's a little hard to demonstrate and stuff, and so mostly you'll see voltage being shared. And to wrap this up, I'm really going to end it here. So I didn't get to the Zener diodes really. We're not going to look at the build, but they're pretty straightforward. You have a power supply, a certain voltage, it has to be above the Zener voltage. And there's a lot of variables. You pick the Zener diode with the voltage you want. So they come in different voltages. That's the voltage they block. Well, reverse bias. So you can see that's the cathode. That's the more negative side. The anode, the more positive side usually. But you use them backwards, because they will pass current like a regular diode if you put them in forward biased. So about 0.7 volts they'll drop, and then they'll let whatever current go through after that. And you reverse bias them, then it's the voltage that you select. So they either have these kind of straight lines or a more slanted lines like that, but that's the general look. And they'll be reverse biased. So they act as release valves. They got a Zener voltage. At a certain voltage, it's going to block current. So it passes along that current, as the voltage over here is higher than it, because it loses a little power through the resistor, so it has to have a higher voltage. But even if the voltage wavers, moves around on this side, the Zener diode, as long as it's still higher, will pass current needed to hold a voltage at its Zener voltage. And so again, the load will vary and it will pass through there. So I may not do another video on that in this series. I've done Zener diode videos before, but this video went long enough, so I'm going to cut it off there. But thanks for watching. I will see you in the next video.